9.4, we deal with two tests for convergence and divergence. And for most of the rest of the test, we're not necessarily going to be looking for what a series converges to. We're just trying to determine does the series converge or diverge. Of course, if it diverges, then there's nothing to find out what it goes to. But if it does converge, sometimes we do want to know what it goes to. But with a lot of these tests, we're not going to be able to find that value. So with a direct comparison test, let's call this a sub n, the series a sub n, which is a series that goes to infinity. If we're trying to show that a series converges, then we want to find a series that's larger than this one. So we want to find some series b sub n. And if we can show that this one converges and that this one is always larger than that one, well, if this is bigger, then it's going to add up to something that's larger. So by default, if this one is smaller and this one doesn't go to infinity, this one's not going to go to infinity either. On the other hand, if we're using the direct comparison test to show that something diverges, if this one diverges, if we can show that a smaller one diverges, so in this case, this one is the smaller one, if it diverges and this one is even bigger, then it will have to diverge as well. Think about if this is infinitely large and that one's even bigger, that one have to be infinitely large also. On the other hand, if this one goes to some particular number and that one's smaller, it goes to a number as well. It's just a smaller number. So let's do the direct comparison test on this one. So often what we do is we try to compare it to a series where we take off all the bells and whistles of this particular sequence and say, okay, if we know what happens to that one, can we show that this one is bigger or smaller? Notice if we take off the +8 and the 3, we have a series here that's a p series with p equal to 3. Since that's greater than 1, then this sequence converges. Remember that p series converge as long as the power is bigger than 1. So if this one is smaller than that one, then it's going to converge also. Well, how does 1 over 3n cubed plus 8, how does that compare to 1 over n cubed? Well, notice that the numerators are the same. So how would this denominator, what could we say about this one to determine whether or not it's bigger or smaller than that one? Well, if we multiply n cubed by 3, then 3n cubed is definitely bigger than n cubed. If we add 8 to it, 3n cubed plus 8 is also bigger than n cubed. So this denominator is bigger than that one. Our n's are positive numbers. So if we have the same numerators but a bigger denominator, then by default, this one is going to be smaller. Think about if we have 1 over 4 compared to 1 over 2. Numerators are the same. If this denominator is bigger, it makes it a smaller fraction. So that's a true statement. So since the bigger one converges, then the smaller one converges as well. Also, another way to show that this inequality is true, that this sequence is always smaller than that one, is if we clear fractions, if we multiply both sides by our common denominator, or cross multiply, we would have n cubed on the left, 3n cubed plus 8 on the right. If we subtract n cubed from both sides, we have 0 on the left, 2n cubed plus 8 on the right. Since n is positive, a positive number cubed is positive, times 2 is positive, plus 8 is positive. So this is always greater than 0 because it's a positive number. So we've shown that that's true. Since that one converges as well. Okay, so let's take a look at this one. So let's try to think about what do we want to compare it to? Do we want to compare it to 1 over n by taking off that plus 3? And let's think about whether or not that would be a good choice. This is a p-series with a power of 1. P-series, p equals 1, that diverges. If p is 1 or smaller, the p-series diverges. But if we compare that to this, if we compare 1 over n to natural log over n plus 3, if this one diverges, we have to show that that one is even bigger. Well, the numerator is going to be bigger most of the time, but what about the denominator? Well, this denominator is bigger, which actually makes the fraction smaller. Remember, if the denominator is bigger, the fraction is smaller. So that leaves in question, well, is this really smaller than that? Because if it was just 1 over n plus 3, that wouldn't be true. 1 over n plus 3 is actually bigger than 1 over n. Bigger denominator makes a smaller fraction. So instead of comparing it to that doesn't really help us. Let's compare it to, not natural log, 1 over n plus 3. So what about that? This is not a p-series, but if we use the integral test, the integral of dx over x plus 3 is natural log absolute value of x plus 3. If technically we're taking the limit, but if we let the upper limit get closer and closer to infinity, natural log of infinity goes towards infinity. So this one diverges. That one diverged also, but we were not able to show by the direct comparison test that diverged also because the bigger denominator actually made that smaller than this one. And if this is smaller, it could still diverge, but we don't know that. In order to show that by comparison that it diverged, we need the smallest one to diverge. If something is bigger than this, it will diverge also. There are many series that are smaller than this that also diverge, but there are also many series smaller than this that converge. All we know is that since this diverges, every bigger one will diverge also. So let's see whether or not natural log of n over n plus 3 is going to be bigger than 1 over n plus 3. Because since this diverges, if this fraction is typically bigger than that one, then when we add these together, we're going to get a bigger value. So if these go to infinity, that one will also. Well, we can clear our fractions, and these are things that you need to show for the test. If you don't show your work, then I'm not going to know how you figured out that was a true statement. Whether you just typed it in your calculator, whether you're just guessing, maybe it's not a true statement. So you need to prove to me that this is a true statement. So there are values for which this is not true, but if we think about when they're equal, when is natural log equal to 1? If we do e to both sides, natural log is equal to 1 when n equals e, when this is e, which e is about 2.71 and so forth, or 2.72. So this is a true statement for any n that's bigger than 3. 3 or bigger. We could say any n bigger than 2, really. Because n is just an integer. So for the first term, this is not bigger. But once we get past the first term, for the second term, and for the third, fourth, fifth, all the other ones are going to be bigger. So if this one diverged and almost all of these terms are even bigger, that one has to diverge also. And we want to tell that it diverges by the direct comparison test. And since we have to show how the direct comparison works, so we have to show what our comparison is, and then we have to show that this one diverges, and then we have to show this inequality to be true. We can't just say, well, this one diverges, so this one does. Well, why does this one diverge? It diverges because this one is bigger than this one. This one diverges, so that one does too. One thing that we do have to be careful about the first two that we didn't mention is that the direct comparison test only works if a sub n, our sequence that's used to generate our series, is greater than 0. If this sequence is negative part of the time, then the direct comparison test doesn't work. So both of the ones we've done so far, this is going to be positive. That is also going to be positive. So it is valid to use the direct comparison test. Now for the limit comparison test, we're making a comparison. So we're going to have another series. And then we're going to take the limit as n goes to infinity of a sub n over b sub n. And we want that limit to exist. Now, if the limit doesn't exist, then we can't use this particular test. We're going to have to find a different one. But if this sequence divided by this sequence has a limit that exists as n goes to infinity, then both series either converge or both series diverge. So both converge or both diverge. So we want to pick something that we can use to compare this to. So let's compare it to the series, let's say 1 over 6 to the n. This is a geometric series. This could also be written as 1/6 raised to the n power, because 1 to the n is 1, 6 to the n is 6 to the n. And since r is 1/6, then that one converges. So we know what this particular series does. So if we can show that when we do this value divided by that one, this sequence divided by that one, that limit exists, then they'll both converge. If we can't show that limit exists, then we're going to have to find a different one to compare it to. So let's do 6 over 6 to the n plus 1 divided by 1 over 6 to the n. So we want to take the limit of this as n goes to infinity. So since we're dividing by a fraction, we can multiply by the reciprocal. Several things we can do here. We could pull this 6 out front. And that's just a constant that's being multiplied. We have 6 to the n over 6 to the n plus 1. Now, if we just take the limit of it right now, 6 to the infinity over 6 to the infinity plus 1 gives us infinity over infinity. times 6, which is indeterminate. So we can use L'Hopital's rule to take this particular limit. We can take the derivative of the numerator, take the derivative of the denominator, and then take the limit again. When we take the derivative here, instead of being e to the u, it's 6 to the u. So like e to the u, it's our base to the n power times the derivative of the exponent. Since our base is not e, we pick up a natural log of our base. Same thing on bottom. The derivative of 6 to the n is 6 to the n times the derivative of the exponent times natural log of the base, and then the derivative of 1 is 0. Well, we have the same thing on top and bottom, which makes 1. The limit as n goes to infinity of a constant is just that constant, so we get 6 times 1, or 6. So our limit exists. So since our limit exists, since the limit of a sub n over b sub n exists, it goes to a particular number, then because the sum of 1 over 6n converges to the series of 6 over 6 to the n plus 1 also converges. So they do the same thing if their limit exists. Okay, we're asked to do limit comparison again. So let's compare this to 1 over n times the square root of n to the 6. Let's just drop that plus 6 off. The square root of n to the 6 is n to the third, because we have our power is 6, our root is 2. 6 divided by 2 is 3. So we could rewrite this as 1 over n times n cubed, or n to the fourth. So this is a series that we're going to compare it with. So if we can show that the limit as n goes to infinity of the first one divided by the second one, if we can show that this limit exists, then whatever this does, this one will do the same thing. So let's rewrite this. Instead of dividing by a fraction, let's multiply by the reciprocal. So this n will reduce with that n. So let's see, what is the limit as n goes to infinity of n cubed over the square root of n to the 6 plus 6. We could do this one several ways. If we just do direct substitution, this is going to be indeterminate. We're going to get infinity on top, infinity on the bottom. And we could use L'Hopital's rule. We could take the derivative of the top, the derivative of the bottom, but that's going to perhaps go on for a little while. The original technique we used was when we were letting n go to infinity, is we divided top and bottom by the biggest power of x, or in this case n. On top, the biggest power is 3. On bottom, the biggest power is 6, but it's under the radical, so that's equivalent to a 3. So we're going to multiply top and bottom by 1 over n cubed. Since this is a square root, we need this to be under a square root, so we can take the square root and square what's underneath. So 1 over n cubed, or the square root of n to the 6, are the same. It's about to die. So 1 over n cubed, or the square root of 1 over n to the 6, are the same. So on top, that n cubed and that n cubed cancel, leaving a 1. If we multiply this times that, that will cancel. We multiply this, we'll be left with 6 over n cubed. So that gives us the limit as n goes to infinity. 1 on top. Under the radical, we said this and that cancel, leaving us 1 When we do this times that, we get 6 over n to the 6th. So now, if we let n go to infinity, the limit of that's a constant, the limit of that's a constant, n goes to infinity, that goes to 0, so we end up with 1. So that limit exists. It doesn't matter what number it is, it just matters that it exists. So since that exists, these are going to do the same thing. This is a p-series because we have n to a power. Our p equals 4, which is greater than 1, so this one converges. If that one converges, then by the limit comparison test, this one converges as well. In Canvas, there's a list of the different tests, so you do need to be familiar with those different tests. You do get to use that sheet, but you need to know how each of the tests work. What are the things you're going to have to show when you're doing those tests? All right, this one doesn't necessarily tell us which test to use. It just says use a test to find out whether we converge or diverge. And they got a whole list of them. They've got probably 6 or 8 different ones. Notice that this series looks like it might be telescoping. If we put in a 1, we get 1 over 7 minus 1 over 8 for the first term. If we put in 2, we get 1 over 8 minus 1 over 9. If we put in a 3, we get 1/9 minus 1/10. 1/10 minus 1/11. 1/11 minus 1/12. So I'm just going to number this as our first, second, third, fourth, fifth. So when we do our second part, we get 1/7 minus 1/9. When we include the third term, those cancel and we get 1/7 minus 1/10. When we include the next one, those cancel, so we get 1/7 minus 1/11. And then when we include the fifth one, those cancel, and we get 1/7 minus 1/12. So a formula of our partial sums is 1/7 minus 1 over n plus 7. Whatever this number is here, it's 7 more than that one. This is 7 more than that one. If we let n go to infinity, as n goes to infinity, that goes to 1/7 minus 0. So 1/7. This converges. Remember, with the telescoping series and the geometric series, we can find out what they actually converge to. If we let our nth partial sum go to infinity, that converges to 1 over 7. And we did that using telescoping series tests.